Have you ever really stopped to wonder what's going on when you cook an egg? Or how a battery actually powers your phone? Well, the answer is all around us, written in a kind of hidden code that pretty much runs the world. Today, we're going to learn how to read that code. We're talking about the language of chemical reactions. Let's dive right in.
So let me ask you this. What on earth could a rusty old nail and a piece of toast possibly have in common? I mean, one is this slow, quiet process of decay, right? And the other is a super fast, delicious transformation. They seem like they're from two different planets, but believe it or not, they share a fundamental secret.
And that's the secret. They are both chemical reactions. Anytime a substance fundamentally changes its identity, you're seeing chemistry in action. And this isn't just stuff for scientists in white lab coats, okay? It's happening right in your kitchen when you cook. It's what happens when grapes ferment into wine, and it's even happening inside you right now as you digest your last meal. It's the engine that drives change, everywhere.
Okay, so if these reactions are happening all the time, how do we spot them? What are the clues we should be looking for? Let's put on our detective hats for a minute and check out the evidence from a couple of really simple experiments.
First up, picture this. You take a simple, shiny ribbon of magnesium metal. Now, what happens when you burn it? Something truly dramatic. It erupts in this dazzling, super bright white flame. It's almost like an old-school camera flash going off. And what's left behind? It's not a metal ribbon anymore. No way. It's a totally new substance, this crumbly white powder called magnesium oxide. A complete and total transformation.
All right, for our next trick, what if we drop a few little zinc granules into a flask with some acid? Well, almost instantly, you'd see this fizz of bubbles rising to the top. That's hydrogen gas being created right before your eyes. And if you were to actually touch the flask, you'd feel it getting warmer. That reaction is literally releasing energy as heat.
So here's the bottom line from our little investigation. These experiments give us our 4 key clues. If you see something change its state, like our solid ribbon turning into a powder, or if it changes color, or if a gas suddenly appears out of nowhere, or if the temperature shoots up or drops down, you can be pretty darn sure you are watching a chemical reaction live and in person.
So, we can see the signs of a reaction, but how do we talk about them? You know, describing every single change in a long sentence would get really clumsy and slow. Scientists needed a better way, a kind of universal shorthand to share these big ideas without wasting time. They basically had to invent a whole new language.
This right here is the old way of doing it. When a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. I mean, it's accurate, sure, but wow, what a mouthful. Not exactly something you can scribble down quickly on a chalkboard, is it?
So, let's build this new language together. First, we take that clunky sentence and we simplify it into what we call a word equation. Think of it just like a recipe. Your ingredients or reactants are on the left, the arrow just means react to produce, and the final dish, the product, is over on the right. It's better, right? But we can make it even cleaner. By swapping the words for their chemical symbols, we get this sleek, universal chemical equation. Mg plus O2 to MgO. Now, anyone, anywhere on the planet who knows chemistry can read this and know exactly what you mean. But there's a catch. And it's a big one. Just writing down the symbols isn't quite enough. See, the universe has this one incredibly strict rule that we are not allowed to break, ever. You can think of it as a rule of cosmic accounting.
And here's the rule. It's called the law of conservation of mass. It sounds fancy, but it's actually pretty simple. You can't just create atoms out of thin air, and you can't make them vanish into nothing. The number of atoms you start with for each element must be the exact same number you end up with. The books have to balance, period.
So let's take a look at this equation for how rust forms. This is what we call a skeletal equation. Let's do a quick head count. On the left, we've got 1 iron atom, but on the right, we have 3. And 1 oxygen on the left, but 4 on the right. Whoops. The books are totally out of whack. This equation is breaking the universe's biggest rule.
So, how do we fix it? Well, we balance it, step by step, just like we're solving a puzzle. Let's start with the most complicated-looking part, that Fe3O4. It's got 4 oxygen atoms. To match that on the left side, we just pop a big 4 in front of the H2O. There. 4 oxygens on the left, 4 on the right. Step 1 is done.
But wait. By putting that 4 there, we now have 8 hydrogen atoms on the left side, but still only 2 on the right. That's not going to work. But no problem. We just put a 4 in front of the H2s on the right.
Now we have 8 hydrogens on both sides. See? We're getting there.
All right, the very last piece of the puzzle is the iron. We've got 3 on the right, but only 1 on the left. Well, that is an easy fix. We just place a 3 in front of the Fe on the left. And, just like that, we're balanced.
Let's look at the final tally, just to be sure. We have 3 iron atoms on both sides. Check. 8 hydrogen atoms on both sides. Check. And 4 oxygen atoms on both sides. Check. The cosmic books are perfectly balanced. Now this is a correct and complete chemical equation.
Now that you've got this skill, we can go way beyond just simple reactions. We can actually start to read the fundamental recipes that run the natural world. And once you can read them, you can start to see the patterns, how some reactions build things up, which we call synthesis, while others break things down, which is called decomposition. It just opens up a whole new level of understanding.
And guess what? This language can get even more descriptive. We can add little symbols to show if something is a solid, a liquid, or a gas. We can even write the specific conditions needed for the reaction, like heat or pressure, right over the arrow. It's all about packing more detail into the story the equation is telling us.
Which brings us to this beast. This is one of the most elegant and, yes, I know, complex-looking recipes in the entire world, photosynthesis. Now, don't get intimidated by all those numbers. Just take a breath. What you're really looking at is the beautifully balanced story of how a plant uses carbon dioxide and water with a little help from sunlight to create glucose. That's its food, and the very oxygen that we're all breathing. This isn't just a random string of symbols. This is the recipe for life on Earth.
So, the next time you see rust on a fence, or watch a cake rise in the oven, or just take a deep breath of fresh air, remember what's really going on. You're not just observing the world anymore, you're reading a story, written in the language of chemistry. Now that you know the basics of this language, what other stories are you going to start to see? What secrets is the world waiting to tell you?